All right, this video is going to walk you through the basics of power and introduce you to the power equation and what power is. So first of all, definition. Power is the rate of energy transfer into, out of, or within a system. So we're talking about work being done, so positive work, energy going into the system, negative work, energy being removed from the system, or energy transformed from one storage mode to another within a system. One of the key ideas here, it's the rate of change of energy. It's how quickly the energy is changing, not how much energy it is. So it's how quickly, not how much. So energy transfer, so the work being done, we can think of it that way, or we can think of it as the rate of transformation. So let's look at the transfer first. So the equation we have for this is power is just the work divided by the time. So how do we calculate work? Well, that's the force parallel to the displacement times the displacement of the object. Or we can also think of the work being done as the force times the displacement times cosine of the angle between them. And this theta is the angle between the force vector and the displacement vector. And then that would give you the work. And then you just divide it by the time. How long did it take to do that work? And that gives you power. Now transformation, this is when all the energy is staying within the system, but it's going from one storage mode to the other. So it's just a change in energy divided by the time for the equation. So very similar. You can think of it either way. It just depends on what you choose your system to be. Neither one of these equations is wrong or very different from the other. It's just a conceptual difference. We usually look at the rate of change of mechanical energy, such as how quickly is the kinetic energy changing. If you are, speeding up, like a car going from 0 to 60, that could be an example of power, how quickly it can do that. Or the rate of change of gravitational energy. So someone running upstairs, how quickly is their gravitational energy changing would give you a rate, would give you their power rating is what we would call that. So what are the units of power? Well, it's the energy divided by time. Remember, work is just change of energy. So it's joules divided by seconds, energy divided by time. And we shorten this to the watt. And so you may have seen this for light bulbs. A 100-watt light bulb is the power rating. It's how many joules per second, how many joules of energy per second that it transforms from electrical to heat and light. So there's the basics of power. Let's do a quick example here. So we lift a 2-kilogram mass. So I got a 2-kilogram mass at a constant speed up 30 centimeters. So constant speed is going to be a key here in a second. So don't lose that. So first attempt. Oh, I can do this real quick. So I'm going to constant speed. Let's say it took me half a second to do that. And now I'm tired, so it's going to take me longer. 1.4 seconds. All right. So I raised it up the same amount, 30 centimeters, the same mass. Except it took, and I did both of them at a constant speed, but they are different constant speeds because it took me a different amount of time. So let's calculate this. So we're going to do the calculation here. So here's our equation for power, where it's the work times divided by the time. So we have to look at what is the force I'm applying to this weight. Well, since I'm going at a constant speed, I know those forces have to be balanced. So the downward force of gravity and the upward force of my pull have to be the same. So this force here is just the upward force of my pull, which is the same as the force of gravity because we're going at a constant speed. So I can just calculate that as the mg, which is the force of gravity, which is the same as my upward force, times the displacement. The d is just a delta y here because we're going vertically, times cosine of 0 because my force is up and the displacement is up. So the angle between them is 0. Notice if we had thought about this as the energy transformation of energy stored gravitationally of our masses in our mass Earth system, well, that would be the change in UG over time. Well, how do we calculate UG? M times G times delta Y. And then this cosine of 0 is just a positive 1, so that doesn't matter anyway. So we get the same result whether we think of it as work over time or change in energy over time. So we run those numbers, and the only difference, so the work is exactly the same on both of them, but the only difference is the time. So I did the same amount of work, same amount of energy, but it took me a different amount of time to do it. So we run the numbers, and the first one we get about 11.76 joules per second. So that's how much energy I am transferring to the masses every second. And that comes out to about 11.76 watts. Another way we could write that is watts, joules per second or watts, either way. Or second attempt took a little bit longer. So it's the same amount of energy though. Same amount of energy, but since it took longer, each second I'm transferring less energy. I'm only transferring about 4.2 joules per second of energy, where the first time it was about 12. So we'd say that's 4.2 watts of energy. All right, that concludes our notes for power.